Hello and welcome to the New York City Category Theory Seminar. It's September 7th. This is our first talk of the fall semester, and we have Sergei Burkin talking about Segal conditions and twisted arrow categories of operads. Take it away.
Thank you. So first I have to introduce myself. I was born and raised in Moscow, Russia. I graduated from High School of Economics, Faculty of Mathematics, got my bachelor's degree and master's degree there. And then I went to Japan. I got my PhD there from Tokyo University. Then I stayed there for 2 years as a visiting researcher, and now I'm not affiliated with any university for a few months now.
Perfect. Good. Now tell us all about twisted arrow categories.
Yes, so twisted arrow categories of operads. First, some.
I just want to say, Icky Merdeic spoke in our seminar 2 years ago about, or 3 years ago, before COVID, about delta. So not delta, Omega. So we know what dendral sets are, but we don't remember anything. So start over. Go on.
Wonderful. So first, brief reminder. I guess you know what a presheave is, what a simplex category is, what is a simplicial set, and what is a nerve of a category. It's the simplicial set that can be defined as follows. So what is important for us is that we can describe the image of the nerve construction in several ways. There are inner-Kahn conditions, strict inner-Kahn conditions, but there are also Segal conditions, and we will be interested in the latter. So this is the condition on a presheave to satisfy the following. We require that for all n greater or equal to 2, the following maps are bijections, where these are the maps induced by the obvious inclusions. And we have that the category of Segal presheaves over delta is equivalent to the category of small categories. And why is this important? This is important because it leads to several definitions of infinity one categories, of which the simplest one is called Segal's category. And Segal's category is just a functor, contravariant functor from delta to the category of spaces, which satisfies the following two conditions. The first is that this space is a discrete space, and it can be thought of as a space of objects. And again, we have that the following maps, they are not required to be bijections, obviously, they are required to be weak equivalences. And this is the weakening of the Segal condition mentioned previously. And as it turns out, this approach works for many other structures.
One second, back up 1 second. What's the weakening?
So we've had this strict
instead of it being bijective?
Bijection, instead we require that, so these things are now spaces and not sets. Well, maybe they are sets, but in general they are spaces. And we require that these maps are weak equivalences.
And this weakening, what does that have to do with a quasi category from
So there is a structure of model category on the category of presheaves over delta with values in sets, which gives quasi categories, and there is a model structure on such presheaves, such that fibrant objects are Segal categories. And these two model categories are Quillen equivalent.
Okay, thank you.
So this is simply, I guess, the simplest way, the simplest of existing definitions of infinity one category. So why is this important? As it turns out, so in general, in mathematics, we have structures like categories, groupoids, commutative monoids, and categories, and also categories ended with factorization systems. These can be thought of as some kind of structures. What do we mean by structure? A structure is that something that is encoded by a special kind of structure, by an operad, a prop, by a Lavie theory maybe, or some other kind of special structure. These special structures are themselves, again, structures. For example, operads, they are encoded by certain operads, by a certain operad. So there is an operad, a very special operad, such that algebras that correspond to this operad are single-colored operads. And there is a special Levy theory, multi-sorted Levy theory, such that the corresponding algebras are the usual single-sorted Levy series. This will be very important in the latter part. And we have homotopy coherent structures. So we take some structure from here and try to relax the relations to get a homotopy coherent structure. So we get infinity one categories, we get infinity groupoids, we get from commutative monoids, we get infinite loop spaces. We also get infinity n categories, we get infinity operads, and so on. So all of these structures, except maybe infinity groupoids, they can be defined as by similar conditions on presheaves with values in spaces of certain categories. So what are these categories? These are categories that are, in some sense, they are very similar to delta.
I'm sorry. So the definition of a Segal condition is not only for delta. You can do it for any category.
Not for any category, for special kind of categories. Okay,
so you're going to explain.
Yes. So here are the main examples. So again, this name Segal, it's because he invented many things. Here we have his name again, but these are not like a Segal category and Segal's category are different things. Anyway, so we have this category gamma, which is equivalent to the category of the opposite of the category of finite pointed sets. And we have corresponding weakly Segal condition, weakly Segal presheaves with contractible space of objects. They correspond to connective spectra. There is a Moerdijk-Weiss dendroidal category omega, such that Segal presheaves over omega, strictly Segal presheaves, so we take presheaves with values in sets, we get operads. And we take weakly Segal presheaves, and we get infinity operads. Recently Hackney, Robertson, and Yao introduced several new categories. So this category, it allows to define cyclic infinity operads. This category allows to define modular infinity operads, and there is also a category that allows to define infinity props. And there are also Jugel's categories theta n that allow us to define infinity n categories. So in all these cases, definitions are similar to the definition of Segal category as a special kind of presheave over delta. So what is the problem with these approaches? So these categories, they were invented by analogy with delta. And first of all, the question is, are definitions of these categories correct in some sense? And as it turns out, no, there are when the situation gets complicated, when the structure is complicated enough, most likely if you try to guess the definition, you will get some minor mistakes in the definition. So you need some general theory that gives you the right category. The second question is, which categories in general admit Segal presheaves? There is a partial answer given by Chu and Hansen in recent work. They say they show that these are the categories that are ended with a certain structure called algebraic pattern. And however, there are many categories ended with algebraic patterns whose Segal presheaves are in some sense wrong. So the categories are fairly natural, but the categories are fairly natural and they are ended with algebraic patterns, but the corresponding Segal presheaves, they are not the structures we actually want to get. So the question is then, what are the right categories? Then where do they come from? And are these categories canonical in some sense? So for example, we can take a delta and remove some objects from it, take just a small part of delta and still define Segal conditions. And this will give us, so strict Segal conditions will give us strict categories. No problem. So we've thrown out some part of this category and we still get categories as Segal presheaves are still categories. But weakly Segal presheaves, they will not be infinity one categories. So the question is why? And can we replace this category with some other category maybe? So some of these questions were asked, I guess first it was Tom Leinster. He gave a talk and then there were several works. The latest one is probably this one, where they try to understand where these categories, including the category delta, first of all, where these categories come from. However, so this work has some limitations. It does not quite explain why these categories appear in homotopy theory, and it requires that the category C, that is analogous to the category delta, it requires that it is a full subcategory of the category of Segal presheaves of a C, which is not always the case in practice. And one can try to fix this. So first of all, one would expect that this inclusion of C into the category of Segal presheaves is just the restriction of the Yenede embedding. But in some cases, this is the case. But there are cases where this is not the case. It is possible to fix this problem and still get such a functor. However, this functor is not full. So in principle, this approach cannot work in this particular case. And also the problem is that to construct C, we have to already know what is the category of Segal presheaves or some equivalent categories. So we already know that we have, I don't know, categories, and from categories we can construct delta, or we have operads and we can construct this Moerdijk-Weiss dendroidal category omega. But the problem is that we do not know what is a colored modular operad what is a colored modular operad is until we construct this category. So we do not know what this is and we do not know what this is, and we have to start somewhere. So again, this approach cannot work in this case. So we need a different solution, and it turns out that most of the above mentioned categories, they can be constructed from operads. And this construction explains where these categories come from, what is their nature, why these categories appear in homotopy theory. It is partially explains. And as it turns out, this construction is the only reasonable generalization of a certain classical construction of Quillen, which is called twisted arrow category of a category. So here are some references. So this is the previously mentioned book. This and this work, they are two independent works. They both introduce this construction, twisted arrow category. And this work is about generalization of cotangent complex. And this work is about Segal presheaves. And here are some examples of works where the authors, they define one category. And as you can see, it can take quite a while to define one category and then to study this high cyclic operads, for example. So now to the definitions. So we can think of categories as a collection of morphisms, and we will represent morphisms not by arrows, as is usually done, but by vertices.
I just want to say, the notion of a twisted arrow was also used in the definition of a coend or an end. You're getting it from a limit. Did that come from Quillen also first?
I don't think so. I guess it was somebody else.
Okay.
Yes, since it was mentioned, I'm not quite sure if these coherent and constructions have natural generalization to the setting of operads. So tweet hetero categories, they have generalization to operads, but this whole coherent calculus probably not. Back to the definition. We can think of categories as a collection of morphisms, and composition will correspond then to a contraction of edges. And the main property we have is that we can contract edges in any order we like. So we have this associativity condition. At the end, we still get the same morphism. Operads are similar structures. So operads, what they have operations. Operations have can have any number of inputs, so 0 inputs, or 1, 2, 3, any number of inputs, but always exactly one output. So this operation, it has 4 inputs and 1 output. Operations have colors. Colors are analogous to objects. So just like morphisms, they have 2 corresponding objects. Operations have corresponding colors. And colors, they determine if we can compose operations. We have composition maps, which allow us to contract edges. And we have also symmetric group actions on operations. So operads, by operads, we will always mean symmetric operads. So we have a symmetric group action on operations, so this structure should satisfy some axioms, which essentially means that if we have such a tree, it doesn't matter in which order we contract edges. At the end, we still get the same operation. And we can also permute, first we can permute, for example, this edge and this edge, this half edge and this half edge. We can permute them to get some other operation here as twisted by the permutation. Or we can compute the full operation here and then permute these 2 edges. Again, we still get the same operation. So we have such axioms. And why do people study operads? Because operads allow to encode algebras. So what can be examples? There is an operad in the category of sets, such that the corresponding algebras are monoids. There is also the operad of commutative monoids. There is an operad in category of vector spaces, such that the corresponding algebras are Lie algebras. And there are many more sophisticated examples, or not very sophisticated. For example, one of the most important operads is the operad of little disks. Perhaps you've heard about it. So what is an algebra for an operad? For each color C, here we have a set, or in general, some object in a category, and we have such maps. So for any operation, we can take, so here we have an operation S, and we have 2 elements of an algebra. We can compute as the output another element of algebra. And we get some element of algebra here, and we get some element of algebra here. And then we can compute here a new element of algebra, and so on. Here at the output, we get finally the final element of algebra. The main axiom of being algebra is that so whether we first compute this step by step and get something here, or whether we first compute the operation by contraction of edges and then apply the resulting operation to the corresponding tuple of elements, at the end we still get the same element of algebra. So this is the definition of an operad. Now, the main definition of this work, twisted arrow category of an opera. Its objects are operations of this operads. Its morphisms, so objects are operations. A morphism from an operation P is an equivalence class of planar rooted trees of height 3 with indexed leaves with exactly one middle vertex marked by the source and without any leaves from the middle vertex. So I will show a picture in a moment. This middle vertex will be called the source vertex. The remaining vertices will be called the non-source vertices. The target is computed by the evaluation, and equivalence is generated by certain permutations. So here is an example. This is an example of a morphism from operation P. It has no leaves attached to it. So any edge connected to this vertex is necessarily connected to some other vertex. And these are two representatives of the same morphism. So what we can do with a representative, we can permute these two edges, for example, or we can permute these three edges. So we've permuted this edge and this edge, and we've got the corresponding vertex here. And here we've acted by the corresponding element of the symmetric group on this operation. And we've permuted these two leaves. And so we've got here permuted leaves, and we've got a new operation here. However, we cannot permute these edges. So these three edges, they are always fixed. And the target is computed by the evaluation of this tree. So we can evaluate this tree to get some operation which will have arity 5. And
Sergei, can you go back now that we saw the picture? Can we go back to the formal definition? I just want to. Okay, so the objects remain the same, and that means so it's more morphisms than there were before. Is that the point?
In classical construction of Quillian of twisted arrow category, it has object, it has morphisms of the category. And for morphisms, it has certain squares, commutative squares. Here we have entirely analogous construction. So morphisms are operations of an operator are analogous to morphisms of a category. So here for objects, we have operations. And for morphisms, we have
so I mean, whoever made up the definition of a twisted arrow category for cohens clearly had seen Quillen stuff before. I don't know what came earlier, what came later, or whatever, but I mean, it's the same type of thing. For every object, there's two morphisms going the opposite direction or something like that.
Yes, exactly. And here we have, so this is a kind of a morphism going in one direction from here. So this is a certain upper part, and this is a certain lower part. So these we again have two kind of separate parts here. So in twisted arrow category, we have a morphism going in one direction and morphism going in another direction. Right. Here, this upper part is analogous to the morphism going in one direction, and the lower part is analogous to the morphism going into the opposite direction. Okay. And so this is a concrete definition. There are more abstract definitions, more natural. And how do we compute the composition? We craft the non-source vertices of F into the corresponding leaves of G, and this gives us a tree of height 5, and we then evaluate certain subtrees that do not contain the source vertex. So here is an example. Here we have a representative of a morphism, and here we have a representative of a morphism. So this is the source, and it will be the source of the composition. And what we do, we take Q1, the first operation from here, and graft it into the first leaf here. So here we have grafted it here. We take the second operation, we graft it into the second leaf here. So we get here a vertex. And the third operation is grafted into the third leaf, so we get it here. And finally, the zeros operation is grafted into the zeros leaf here. So we get the following vertex. So we've got this tree of height 5. And what we do next, we evaluate the maximal subtrees that do not contain this vertex. So we evaluate this subtree. So this is P1, we graft it into it Q3, and then Q1. We get this operation. With P2, we do not have to do anything here. And here we again compute this subtree, and we get this operation. And this is the representative of the composition. So this is a concrete definition. Here are some examples of computation. So there is an operad which has exactly one color, and for each RTN, it has exactly one operation, μ. This is the operad whose algebras are commutative monoids. And composition there is only one way to define composition in this case. And what we have that the corresponding Pistitero category of this operad is equivalent to Segal's category gamma, the opposite of the category of finite pointed sets. And how does this equivalence work? What we do, we send an operation, an object in here, we send to the object here on n+1 elements. And at 3, T is sent to the opposite of a certain set map F, such that pre-images of any element I, it is the set of indices of leaves of the vertex attached to the ith edge of the source vertex. So here is a concrete example of computation. So this is the source vertex of some morphism. And it corresponds to the map, to the opposite of the map from a set with 7 elements from 0 to 6, because we have RT6 here, to the set with 3 elements from 0 to 2, because we have here, we have the source has RT2. So this is this corresponds to the opposite of a certain set map, such that the preimage of 0 is 0, 6, 2, and 4. Preimage of 1 is 3, 5, and 1, and preimage of 2 is empty. And once we have such a description, this picture, it is fairly obvious that the equivalence holds, that the composition of morphisms corresponds to composition. Second example, there is a single-colored operad whose algebras are monoids. How does it work? We have for each RTN, the corresponding operations are elements of a symmetric group Sn. Symmetric group acts freely on this set. Each set contains a distinguished element, μn, and the composition of these distinguished elements is a distinguished element. And we have that twisted arrow category of this operad is equivalent to delta. And how do we prove this? First of all, any object mu and sigma. So this is operation. Any object is an operation. In general, operations they look like this in this operad. So this is some distinguished object shifted by some permutation. We have that any object is isomorphic to this distinguished operation μn. The non-source vertices of this isomorphism are marked by the identity operation, and leaves are permuted according to the permutation sigma. So this is a fairly trivial morphism. and it is an isomorphism. So we get that the full subcategory on these distinguished operations is the skeleton of this category. And since the action of symmetric groups is free, any morphism in this category has a unique representative with all vertices marked by these distinguished operations. So recall that we can permute these half edges above this operation and half edges above this operation in any way we like, and we still get a representative. Since the action of symmetric group is free, in the cases that we consider, there is exactly one permutation of all these edges such that we get, so in this case, we should get a distinguished element here, 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 and here. What we can do next, we can evaluate this tree. We get that the target is an operation man. And again, by using the fact that the action of a symmetric group on operations is free, we get that the permutation of all leaves above the representative tree is trivial. So what we get correspondence between, we get that this full subcategory, every morphism has unique representative that corresponds to planetary. That is not marked by anything, and which has H3. On morphisms, then, so what we do, how the equivalence works, we send this operation man to n. And on morphisms, Fi is the index of the leaf that follows in the counterclockwise direction after the edge that attaches the i's non-source vertex to the source vertex. So here is a concrete example of computation. As I've explained, any morphism in this full subcategory A has unique representative that is a planet tree of H3 with trivial permutation on all leaves. And then this morphism, it corresponds to the morphism from 3 to 5, because we have arity 3 here and arity 5 in the target. We have that F0, so this is a zeroth edge of the source vertex. It is sent to this, to 1, because this is the next leaf in the counterclockwise direction. 1 is sent to 3, and 2 is sent again to 3, and 3 is sent to 4. So again, this description, it makes the remaining part of the proof trivial. Another example, there is a certain colored operads as op. Its colors are natural numbers, and its algebras are single-colored operads. Its operations are planar rooted trees of any height, with permutation on leaves and permutation on vertices. And composition, what it does, it inserts the tree Q into the i's vertex, so we have I here, into the i's vertex of P. And for a picture, so there is a slightly more complicated operad, because algebras are the so-called modular operads. Its operations are not necessarily trees, but graphs in general, with linear order on leaves, on half edges of each vertex and on vertices. And composition is again insertion. So here is a concrete example of computation of composition in this operad of modular operads. We take this graph and we insert it into the second vertex of this graph. So what do we get? This subgraph here corresponds to this graph. And we have that. So this vertex corresponds to this vertex. And this loop is this small loop. And we have that first leaf here, it should attach itself. So first of all, there is a zeroth leaf. Here, it should attach itself to the zeroth leaf here. So this is zeroth leaf here. We have that, we get the corresponding edge here. First leaf here, it should attach itself to this edge. So we get this edge. And here it is connected to here, the second leaf here, because it is attached again to this edge. And so on. We have the following composition. And so the operator of symmetric operads, it has a similar description, except we have rooted trees, not any graphs, just rooted trees. And we have the following. We have that the twisted arrow category of this operad, it is equivalent to Moerdijk-Weiss dendroidal category omega. What is this category? It is the category generated by free operads on trees. So trees, they also allow to generate a free operad that corresponds to a tree, and we get the following category. And however, we will not actually need the concrete description of this category. And we also get that this category is almost equivalent to a graphical category of Hacknick-Robertson-Yeo that corresponds, that encodes modulo operads. So almost here means that we should change, we should introduce a minor change in the definition here. To the next part. Why are these twisted arrow categories of operads, why are these categories important? Because they allow us to define Segal presheaves. And how do we define these Segal presheaves? We have a notion of an upper morphism. It is a morphism with only upper non-source vertices being non-trivial. So what this means is that in a morphism here, we require that this vertex is trivial, so it has arity 1. So this vertex here in this picture has arity 3, but we require that actually it has arity 1, and it is marked by the identity operation. So we get that only these non-source vertices can be non-trivial. This gives us the notion of an upper morphism. And we have the corresponding notion of a lower morphism, such that only the lower vertex is allowed to be non-trivial. So upper vertices, they should have arity 1. They should be marked by the identity operations. And additionally, we require that the indices of leaves of upper vertices increase in planar order. We do not require that all leaves increase in planar order, but only the indices of leaves above the upper vertices. Why is this so important? Because any morphism in twisted arrow category of any operad, it can be factored uniquely as an upper morphism followed by a lower morphism. And this is fairly easy to see. And moreover, upper morphisms, they form a subcategory, and lower morphisms form a subcategory. And this gives us a strict factorization system. So a strict factorization system on a category C is a pair of two subcategories, such as any morphism can be factored uniquely as a morphism from the first subcategory followed by a morphism from the second subcategory. Any strict factorization system generates orthogonal factorization system, and in this case, it is natural to call this factorization system active inert factorization system. And if you are familiar with concrete examples in, I don't know, delta, gamma, theta, and any other examples, so This is entirely analogous to that situation.
What's an orthogonal factorization system?
Orthogonal factorization system is a pair of subcategories such that any morphism can be factored uniquely up to unique isomorphism of factorizations.
So regular factorization could be factorized many different ways, but this is unique.
Yes, so there are like three notions that people encounter. There are weak factorization systems such that the isomorphism is not required to be unique. There are orthogonal factorization systems where we require that the isomorphism is unique. And there are strict factorization systems where we simply require that factorization is unique.
Okay, thank you.
We have two special notions. There is an input map. Any operation has n. Operation of arity n has n input maps. So this is a lower map. This is a lower map from identity operation to P. So this is it will be represented by tree whose source is vertex of arity 1. The upper vertex will be marked by identity. The source will be marked by identity, and only the lower vertex will be non-trivial. And we have another special kind of morphism as the output map. It is the only upper map from the identity operation to P. So this structure is precisely what allows us to define Segal presheaves. First, we introduce a simple notion of single object Segal presheave. The single object Segal presheave X over twisted arrow category of an operand P is a presheave such that for any operation P, the product map, which is what you've seen in the first slide, so this is more or less analogous, except we do not consider X0 now. We consider only operations of arity 1 here, trivial operations of arity 1. So we have this map. We require this map to be a bijection. And in particular, for any operation P of arity 0, we have that the set XP is a singleton. And we have that for any set operand P, the category of single object, Segal presheaves of a twisted arrow category of P, is equivalent to the category of P algebras. And there is a very concrete way how this correspondence works. And I will perhaps skip the proof, but it comes, so the hardest part is this diagram, and it is not that complicated, actually. It implies this diagram, which implies that one of the main axioms of algebra. So it implies that we get an algebra from a presheave. So a concrete way how we construct a presheave from an algebra, we define XP to be the product of these sets where P is an operation with input colors C1, Cn. And so these presheave maps, they correspond to products of algebra structure maps that correspond to upper vertices here. So the tree above, so this tree, it sends a tuple of elements of A like this. It sends it to a tuple of elements here. So we apply P1 to A3 and A5. We apply P2 to the empty list. We apply P3 to A1, and we get a tuple of 3 elements here, which is an element of XP, because P has arities 3. So this is a fairly concrete equivalence. And here is a full definition of Segal presheave. We have what is called a petal map, which is a lower morphism from an operation of arity 0. We have full subcategory of the category of lower maps. the full subcategory of on identity operations and operations of arity 0. The only non-trivial maps in this subcategory are petal maps. So the only non-trivial maps here are the maps from operations of arity 0. The maps from identity operations are always trivial. And there are two possible definitions of Segal presheaves. The first is essentially it is due to Chu and Hansen. It is entirely analogous to what they do. This is the condition on the restriction of this presheaf to the subcategory of lower morphisms. This is the condition to be a right kind extension along the inclusion of this full subcategory on identity operations and operations of arity 0 into this subcategory of lower morphisms. The second version is a certain sheaf condition, again, on the restriction of this presheaf to the subcategory of lower morphisms. So this is, again, entirely analogous. This generalizes what happens in the case of delta. Moreover, these two versions, they are equivalent under mild assumptions on operad P, and these always hold in practice. And instead of lower morphisms, we can consider inert morphisms, nothing changes. So this is how we define Segal presheaves, and obviously this allows us to define weakly Segal presheaves, but then we run into the question, is this definition even correct? Okay, we have a right to some definition. Why is it correct? Why is it meaningful? Maybe we want, what we actually want is something else. We want to understand the connection between this construction and homotopy theory. So there are two connections, actually. One is given by the following theorem proposition. If the category of operations of arity 1, so for any operad P, there is a corresponding category of operations of arity 1. If this category is a groupoid, then the corresponding twisted arrow category of this operad has a generalized 3D structure. In fact, if we require that the degree map, so generalized 3D structure is a certain structure, part of which is a certain map called degree map. If we require that this degree map is given by the arity operations, then we get if and only if we get this that this is a generalized 3D structure if and only if this category is a groupoid. So why generalized 3D categories are important? Because if a category S has a generalized 3D structure and a category C is a cofibrantly generated model category, then the functor category has a model category structure. And in fact, what people usually want in concrete examples, not model structure on this category, but actually model structure on presheaves. So we want contravariant functors for which we need to check if this generalized 3D structure is dualizable, and it is possible to do this, but I will not go into details. So this gives us one connection to homotopy theory of these categories. There is another connection, and first of all, there is a more abstract definition of this notion of twisted arrow category. So any category first, why is in which sense this construction is a generalization of twisted arrow category construction? In the following sense, any category can be seen as an operad with all operations having arity 1. Then the construction that we've introduced today, it is exactly the twisted arrow construction of Quillen. And it is known that this construction, this category, it belongs to the following sequence of categories. And as it turns out, for any operad P, we have entirely analogous sequence. So this category delta for categories, it serves the same purpose as category omega for operads. So these two things here, they are analogous. This is what is called a universal category, universal enveloping category of an operad. It was introduced by Ginsburg and Kapranov in 90s. And this is the last category here is the category of operators. It was introduced, I guess, by May in the 60s. So May have these two sequences. However, as we explained before, this category here and this category here, they are actually twisted arrow categories of operads. So what we actually have, we have the following two sequences. So here is a twisted arrow category of an operad, and here is a twisted arrow category of an operad. And so this leads to another definition where here, so an operad P is a Segal presheave over this category here. And as it was explained, any algebra, so for any operad P, any algebra of A over P can be seen as a single object Segal presheave. So here we have the corresponding single object Segal presheave, and we can take the slice category here. And here is, again, a classical notion due to Ginsburg and Kapranov. And it turns out there is a category here, a natural notion that belongs to this sequence, which should be called a twisted arrow category of an algebra. And we have the following two probabilities. We have that this functor here, and in particular this functor here and this functor here. So this third sequence is a generalization of these two sequences. And we have that this functor here and this functor here and this functor here, they are discrete op vibrations, which gives us one abstract definition. Because if we have some target category and we have a discrete op vibration, we know, so discrete op vibrations, they correspond to functors with values in sets. This corresponds, so this discrete op vibration here, it corresponds to functor from this category. This is just the home functor. And this category here, it corresponds to a certain functor from this category, which is entirely analogous to the home functor. And in general, this gives us one abstract definition of this construction that is related to certain classical well-known construction. And we also have that this functor here, this functor here, and this functor here, these functors are localizations by the apomorphisms, which gives us, up to equivalence of categories, this gives us a second abstract definition of this construction. And there is a third abstract definition. There is a classical construction due to Bayes and Dolan. So for any algebra A over an operad P, there is the corresponding operad called the plus construction, such that algebras are precisely the P algebras over A. There is another construction called universal enveloping operad, such that corresponding algebras are the P algebras under A. And there is a notion, it turns out that there is a notion of twisted arrow operad of A, which is the operad such that algebras are P algebras that are both under A and over A in a compatible way. So we require that the composition is identity. So what we have actually is that this new notion is just the composition of these notions from 90s. And what we have is that, so this notion due to Ginsburg and Kapranov, it is just the category of operations of arity 1 of this operad here. And it turns out that this category, so this gives us a third definition. This category here is the category of operations of arity 1 of this operad. So objects are elements of this algebra, morphisms are equivalence classes of certain expressions here. And composition can be computed, it can be described in concrete way here. And the problem is that morphisms are equivalence classes of these expressions. In general, it is hard for any, for a general operad P, it is hard to compute this category. And here we have a concrete description of this localization functor that I've mentioned previously. So this is an element of a Segal presheave here over an object P. So single object presheaves, they have tuples of elements. So P has RTN, and we have a tuple of elements here. This element of this category is sent to an object of this category. So it is sent to an element of an algebra that is computed by applying this operation P to this tuple. And on morphisms, what we have that this morphism here, so this is just a morphism in this category, together with this tuple of elements from the algebra. It is sent to this expression here. So here we have P0, P here, P1, and so on. So this is just the expression that corresponds to this tree. And it turns out that this is the localization by the upper morphism. So the problem is that this category can be hard to compute in general. And to compute it, we have to introduce the following notion. An operad P is canonically decomposable by a certain subset P prime if we have the following. If we have that for any operation P of non-zero arity, there is a unique operation P prime in this subset, unique operations P2, Pn in this operad, and unique indices such that the following equality holds. So in this first place, we require that we have identity operation and index 1. And here we require that we have these unique operations. If any operation of an operad P can be decomposed uniquely as a decomposition, so this corresponds to tree of height 2, which with one lowest vertex, which is marked by P prime, with the first upper vertex marked by identity operation, with the remaining vertices marked by operations P2 to Pn, and with a certain permutation on leaves, which corresponds to these indices here. We require that any operation P has a unique decomposition like this. And if an operad P is canonically decomposable, then any morphism has a unique representative of the following form, where this operation is operation P prime. So why is this important? This allows us to compute these categories in practice. For example, so the main example is that this operad of operads, it is canonically decomposable. With this set P prime, it consists precisely of trees of height 3 with one middle vertex, which is required to be the first vertex. It has no leaves. It has one, in this tree has one lower vertex, and it has some upper vertices. So I will keep the example. So what is important is that the concrete definition that we've had in the beginning, it comes from this property of this operad. So this very concrete definition, it comes from this abstract from the abstract definitions, and it is the concrete description. It comes from this property of this operad. And why is this property so important? Because if an operad P is canonically decomposable, then for any P algebra A, this functor, it is not merely a localization, it is actually an infinity localization. So in general, an infinity localization of a category is an infinity one category. But here we have that this is, so if we take infinity localization by the apomorphisms, if an operad P is canonically decomposable, then we get a category, not merely an infinity one category, but actually a category. And operads of monoids, of commutative monoids, the operad of operads and the operad of modular operads, all these operads are canonically decomposable. So in particular, we get that this functor is not merely a localization, but actually an infinity localization for any operad P. And the two particular cases for the operad of monoids here and for the operad of commutative monoids, which can be skipped here. These two cases, that these are infinity localizations, it was proved in the work of Taschewald. These are the main theorems in one of his works. And we also have that this functor is infinity localization. We get a kind of recursive justification of why this category omega is in a certain sense correct. So this category, it generates all the other categories, all the other twisted categories by infinity localizations. And in particular, it generates itself. And why is this so important? Because props, so the structure of prop and the structure of a properad, both of these structures can be described by operads. So there is an operad such that the corresponding algebras are single-colored props. And there is an operad such that the corresponding algebras are properads, single-colored properads. These two operads, they are not canonically decomposable. And in general, the functor, so the entirely, so particular case of the general functor mentioned previously, in general, this functor is not an infinity localization. So here we have the operad of properads, and here we have some properad, which encodes some structure. We have that this functor is not an infinity localization. Why is this important? Suppose we want to define the notion of infinity one category ended with a factorization system. So we want some homotopy coherent structure. The strict structure, the structure of a category ended with a strict factorization system, it is encoded by a certain prop. Let's call it P. The natural way to try to define this homotopy coherent structure is to define it as a weakly Segal presheaf over this category, which can be done. So it is possible to define weakly Segal presheaf, so with the hetero category of props. No problem here. The problem is that we have then to check that this functor is infinity localization, because in general it is not an infinity localization. And if we define this structure as a weakly Segal presheaf of this category, maybe this definition will be wrong. So we have so.
How much longer do you have? How many more?
10 minutes. 10 minutes maybe.
Okay.
So here we could define, we can define infinity one categories as weakly Segal presheaf of these categories, precisely because this functor is infinity localization. And we can define infinity operads as weakly Segal presheafs of this category, precisely because this functor is infinity localization. This is the content of my previous book, and there is an upcoming book, not yet published anywhere, not yet in archive, However, I've tried to generalize this construction to finite product operads, which are equivalent, which are the structures that are equivalent to Levy series. There are some structures that can be encoded by finite product operads, but cannot be encoded by usual symmetric operads. For example, groups, they can be encoded by Levy series, they cannot be encoded by operads. And finite product operads themselves, so single-sorted finite product operads, they can be encoded by certain finite product operad. So the question, does this theory, can it be generalized to finite product operads? So what we get is that so far I've found two reasonable generalizations. The first construction, it gives us a category. So we take a finite product operad, we get a category. And if you think, so these are equivalent to Levy series, but here, so Levy series is a category of a very special kind, but this category here is not this category, it is something else. So this is the first construction. The second construction, it actually produces not a category, but a 2-1 category. And in some sense, it seems that this second construction is more natural. In the second case, in particular, the definition of Segal conditions is in a certain way simpler than in the first case for the first construction. And I guess I have a proof, but I need to check this. But it seems that the category or 2-1 category that corresponds to the finite product operad of monoids is not equivalent to delta. So why is this important? Because it would be really nice if we had some, if we could say that delta is the category that corresponds to associative structure. This associative structure maybe can be encoded by an operad, by a Levy series, by a modad, by some other kind of structure, but in all these cases, we can do something with these structures, and in all these cases, we get, at the end, we get delta. However, it seems that this is simply not the case. And for the finite product operad of groups, we do not get the category of finite non-empty sets, which is, in some sense, should be analogous to delta when we consider groupoids. So this situation is very different from this work I've mentioned previously, because what they do, they get this category and this category from certain monads. And here also I'll mention briefly what I would like to do next. I would like to generalize this to infinity operads. And Truong Hoang, so this is, he wrote an independent work. He considers this generalization to infinity operads. Actually, there he considers infinity operads modeled by operads in the category of simplicial sets. And I would like to define this structure for operads modeled by dendroidal sets. There should be also connection between twisted arrow categories of little tubes operads and GL's categories theta n. So there are categories theta n which allow to define infinity n categories as weakly Segal presheaves over these categories. And there is some connection between these categories and little disks operads, but it is not clear what is the precise connection between this structure, this infinity one category, and these categories. And there is also, so we've defined this infinity localization. It gives a fairly obvious connection to existing approaches to infinity operads and their algebras. So this category here, it allows to define algebras over operad, infinity algebras over operad P. And this structure here, it allows to define infinity algebras over P. So there should be a fairly straightforward connection between two approaches. Thank you.
Thank you very much. It's a lot. Somebody in the chat asked, what's the name of the books? The book that you did write and the book that you, well, he asked what we will write.
Article, so here. So this is this paper.
Just came out, right. Okay, very nice. Very nice. 65 pages. Any other questions?
It is 65 pages, but most like the core is actually much simpler than 65 pages, maybe 20 pages or so.
Very nice. Thank you. Any other questions? Okay, so let's thank the speaker again. Thank you very much, Sergei. Nice meeting you.
Thank you.
Next week we're going to have Prakash is going to speak about quantitative equational logic. So you're all welcome to join in. Anyways, Sergei, good luck. Thank you very much.
Thank you.
Okay, very nice, very clear. Take care. Good night, everybody. Take care.